Now we will learn where to position the sampling nozzle in the process flow diagram. This is the first step in the process sampling system designed to determine where are we going to get the sample from in our process to achieve best and most efficient performance. There are two steps in determining the exact location of the sample nozzle. The first step is to decide on the process flow diagram the sample tap location, where the intended measurement is required. The second step is to determine the exact position of the nozzle on the line or vessel on the mechanical drawings. First of all, we have to answer this question to properly select and evaluate a tap location. The first question is, what does the analyzer measure? You have to understand the application. Make sure you know what you need to measure and the range of measurement. Knowing that will allow you to focus on what happens to the analyte as the process fluid travels on its way to the tap location. It's important to know why the measurement is important. There are two reasons for making an online analytical measurement. First reason is to find out what the process just did, so the operator can react to it in some way by manual or automatic feedback control. In this case, we focus on what happens in the process fluid upstream of our tap location before we measure it. Second reason is to determine what fluid composition is going to the next process unit, shipping it to a customer or discharging into the environment. In this case, we focus on what happens to the process fluid downstream of your tap location after you measure it. Question 3 is, where is the ideal place? Where would you sample it if you could? Rarely is anyone interested in the fluid flowing in pipe or a duct because nothing is happening there. More important is what the process is doing inside a reactor or a separation tower or a fractionator. That's where all the action happens. There is an ideal place inside the process where the measurement is truly desired, but for practical reasons the sampling tap is located elsewhere, usually downstream of the process, to be monitored or controlled. Therefore, something could happen to the sample as it flows through the process vessels and piping in between this ideal place and the practical tap point. Question 4 is, what happens to the sample? Evaluate the path taken by the sample fluid from the ideal place to the actual tap location. Once you have located the real source of the analyzed sample, it's relatively easy to determine what happens to the fluid on its way to the sample tap. Focus on 2 points. How long does the process fluid takes to get there? The delay can be 0 or it could be enormous. On its way to the nozzle, does anything happen to the process fluid that might change its composition or the physical property we need to measure? Let us focus more on these 2 points. How long does the process fluid takes to get to the sample tap? It is important to locate the sample tap where corrective action may best be achieved in the process. Locations downstream of large vessels or accumulators should be avoided due to an increase in lag time that is introduced by the significant volume increase. Locate the analyzer as near as practical to the sample point to minimize sample transport time. It's best to follow the actual process piping on site rather than on a schematic. If the unit is still in the detailed design and engineering stage, try to get access to three-dimensional model. Look for large vessels or long pipelines between the source of the sample and the tapping point that act as a mixing volume that can cause significant delay for the fresh sample from reaching the sample tap. In your evaluation, be aware that gas and liquid streams behave differently in industrial processes. Gas streams tend to move at high speed and their time delay in pipelines and vessels are usually negligible, but it be significant if gas is at high pressure or vessel is large. For liquid streams are more likely to suffer severe time delay because liquid accumulate in the bottom of process vessels and often flow slower than gases do. Generally, process tanks, liquid separator, knockout drums, absorbers and other high-volume vessels are not acceptable in the line between the sample source and its tap. You can estimate the delay in process vessel by dividing 3 times the containing fluid volume by the process flow rate. The second point we need to focus on is, does anything happen to the process fluid that might change its composition on the way of the sample from its source to the process tap? In addition to the inevitable time delay, the composition of the process fluid may change on its way to the tap. Fractionation, contamination or chemical reaction can change the concentration of the sample or introduce a new substance to it. The most likely cause of composition error is process fractionation. This occurs when a liquid mixture and its vapor are present in the same space, as in a separating drum. Usually, the vapor and liquid have separate outlets from that kind of vessel. Unfortunately, they also have different compositions. The same problem exists when a vapor is beginning to condense inside the process line upstream of your tap. Consider the overhead vapor from the distillation tower. For instance, the vapor leaving the tower is saturated. If the pipe is colder than the vapor dew point, the vapor will start to condense, and small drops of liquid will form. Dead legs in process piping can be also a source of contamination. Any contamination of the measured stream by another fluid is unacceptable even if the intruder is plant nitrogen or water. When a closed process is holding back a pressure greater than the measured stream, the risk of leakage and contamination is too high to accept. Move the tap upstream of the pipe junction or upgrade the process valve to be double block and bleed arrangement. Another reason for composition change is chemical reaction. Any chemical reaction that involves the analyte and occurs prior to the sample tap location will invalidate the extracted sample. Now we will discuss some ideas that can optimize our selection process for tap location. The first idea is that we try to make the process work for us. Plants are excellent fluid conditioning machines, so the condition of the fluid often improves as it moves downstream. Hot fluids will cool down, mixed phases will separate or unify, process fluids will carry less solid matter. So, unless you really need a very fast response, always look for better tapping point further down the process flow diagram as long as, and this is important, the required composition or physical property that we need to measure is not affected and the delay in the measurement is acceptable. The second point is pressure. The ideal process nozzle provides just enough pressure to drive the sample to the analyzer and onward to its disposal. Insufficient pressure condemns you to use sample pumps. Sample pumps are expensive, especially in explosive atmosphere such as petrochemical processing plants and refineries. Also, sample pumps are a significant maintenance liability. Use sample pumps only after exhausting all other options. A system driven by process pressure is cheaper and more reliable. Another important thing regarding pressure, don't select supply and return nozzles that bypass a process flow valve or process flow sensor, as you might degrade the performance of a process control loop. Sample and return points around control valves present two problems. The first problem is that the sample bypasses the valve when it should be closed. The second problem, that there is little or no sample bypass flow when the control valve is wide open. The third point is temperature. Try to find a sample point that's cool enough for the analyzer, avoiding the need for a sample heat exchanger. Gas streams are sometimes at a very high temperature and may require special materials of construction or even a water-cooled probe. Another idea is to locate the sample tap for ease of cleaning or maintenance and means of access to the sample point. Sample taps should be located such that hydraulic cranes, man lifts or ladders are not required to reach them. All else considered, locate the sample tapping as close to the analyzer as possible. Long sample transport lines are expensive to install.